given a basis, there will be components of that also. Okay. Now, maybe this entire thing looks very abstract at this moment, but we have defined it. Let's try to make some sense out of this. When I say that I am not sending any one form, I am not sending any vectors, I am getting a scalar. What does it mean? I must at least zero. So this must. So I don't send this any one forms. I don't send any vectors, but I get a scalar, which means this itself should be a scalar. Okay, so a tensor of 0, 0 rank, 0 rank is a scalar. Okay, so we have scalar is a tensor of rank. I will write in both notations 0, 0 or 0. 0 is 0 plus 0. Now if I send a one form, I get a scalar, then what should this be? This should be a vector. So this tensor will be a vector. If I am only sending one form and I get a scalar, then this is a vector. If I get one vector and I get a scalar, this should be one form. So both one forms and vectors are tensors of rank 1. Okay, but I have to differentiate here. So a vector is a tensor of rank 1, 0 or 1. In this sense, both are same. Similarly, a one form is a tensor of rank 0, 1 or 1.
So I think you have used M for one form and N for first index is for one form.
Correct. That's correct. See, I am sending a one form, I should get a scalar, that means tensor should be a vector. So we have two distinct first rank tensors, vectors and one forms. Okay, one form is also a first rank tensor, vector is also a first rank tensor. Scalar is a tensor of rank 0. Now we can have second rank. What can be second rank tensor? I send two one forms, get a scalar, or two vectors and get a scalar, or one form and one vector and get a scalar. So there are three varieties in which I do. So rank 2 tensors they are of the following type. 2, 0 implies a linear scalar valued function, a linear scalar valued function of two one forms. Zero comma 2 is a linear scalar valued function of a linear scalar valued function two vectors. And then I have 1, comma 1. That is 1 form and 1 vector. Okay, it's a linear scalar value function of 1 form and 1 vector. And we can go on writing like this, any tensors, and you will see that these things can be, they are all isomorphic to each other. A linear functional like this, you can have a set of linear functionals of this type, which will also form a vector space. You will have a set of linear functions of this type, set of linear functions of this type. They will all be isomorphic to each other. So vector spaces of linear functionals or tensors of a given rank will be isomorphic, independent of whether we are sending one form, one form, or one vector, two vectors, two one forms. It is easy to understand if you don't differentiate between vectors and one forms. But even if you differentiate between vectors and one forms, which is true in some curved geometries, there is an isomorphism.
So you have the three things.
Yeah.
In case of vector spaces, you have a vector space and dual space.
Yeah.
You gave some examples.
Yeah.
In the case of second rank tensors, you have got three isomorphic objects.
Correct.
Is there any example for example?
Yeah, I will give you some example. See, for example, let me take, so let me define an important tensor here.
Sir, what the exact definition for isomorphism?
Isomorphism means if you have two vector spaces, so let me say isomorphism. Isomorphism means you have a vector space V, another vector space V prime, then I can define a transformation from this vector space to this vector space such that the T is 1, 1 and on. That means it is a bijective mapping between V and V prime. Homomorphism means it's only onto, it's not 1, 1. But isomorphism means it is 1, 1. Okay, so there is an important tensor that I will define now. This is called metric tensor. Metric tensor is defined as, we define it as G. So it's a special tensor. It is a special tensor of this rank 0, 2. That means two vectors are given as input and we get a scale. That means I am going to have two vectors A, comma B, which is equal to simply A dot B. G of A, comma B is simply A dot B. This is an important tensor. For example, if I have A is defined as A alpha, E alpha. because this is a vector, I'm writing the contravariant components of the vector. And B as, you can write B beta, B beta. Now I can write, see, maybe it is better if I write it in one context completely, then it will be clear. So let me write this as G of A1 E1 plus A2 E2 plus A3 E3. Let's assume 3 coordinates. Similarly, B1 E1 plus B2 E2 plus B3 E3. Now this E1, E2, E3 assume that they are orthogonal. Okay, if they are orthogonal, then what happens by linearity? I can split them into pairs of E1, E1, E2, E2, etc. And E1 dot E1 alone will give you non-zero result, because finally we will write this as A1 B1 into G of E1 comma E1. E1 comma E1 is by definition E1 dot E1, which is equal to 1. E1 dot E2 is 0 and so on. So you will get A1 B1, A2 B2, A3 B3, etc. So I think this is, so let me write it directly. Plus A2 B2 plus A3 B3. This is the result, but what is G itself? So I can define this G G alpha beta as G of, these are components, G of E alpha comma E beta. G of E alpha comma E beta. But this is nothing but, if E alpha and if this basis is an orthogonal basis, so this is simply delta. So this is nothing but this is an identity matrix called as delta alpha beta. If alpha is equal to beta, then we have
earlier you wrote one of the indices as superscript in chronological.
yeah.
Now it's like, so is there any difference?
Yeah, the difference is earlier, so what was the context in which I wrote that delta?
Between dual space and scalar product.
Yeah, so there what I was doing is you have an alpha and beta. Okay, this is the definition of the dual basis. This I wrote it as delta alpha beta. So this is in the superscript, this is the subscript. But these are two vectors. Okay. But here I have a component of the second rank tensor. Whereas these are just first rank tensors. This is also a second rank tensor, but this is a second rank. So second rank tensors will give you a scalar depending on whether you are having one vector and one scalar. So essentially, this is a second rank tensor of 1-1 type, because two vectors are going as input. This is a one form and this is a vector. So you get this as a 1-1 type second rank tensor. Whereas this is 0-2 type, because two vectors are going inside, you are getting a scalar. So this delta alpha beta is a 0-2 type second rank tensor. This is In other words, this is called a mixed tensor. Second rank again. Because one form, one vector are going as input.
You call these two objects as chronicle delta?
Yes. There are, see, chronicle delta is a general term. Okay, chronicle delta simply defines that when you have two indices, if any two indices are same, if the two indices are same, it is 1. They are not same, it is 0. But within that chronicle delta, I can also define, see, delta alpha beta is 0, 2 type. And delta alpha beta is 2, 0 type. And delta alpha beta is 1, 1. So chronicle delta itself is a second rank tensor. So we write 0, 2 type in this way, 2, 0 type in this way, 1, 1 type in this way. It is very easy to understand. In this, what I defined earlier, these two are inputs. One is a one form, other is a vector. So I should have a mixed tensor. In this, both are vectors. So I will have delta alpha beta.
This second case where we have two unformed sensing, is there any such is it relevant in physics, just like metric tensor?
Yeah. Yeah, basically you can always have, see, metric tensor is not this.
No, but
Yeah, so you can always ask this question, what is the G of E alpha comma E beta? This becomes, so you call this as G alpha beta as equal to this, which is nothing but delta alpha. See, sometimes this is just a notation, but just to keep that discipline of respecting the positions of those indices, we define these three different chronicle deltas. Because see, these are, what are these things? These are your reciprocal lattice vectors. These are your dual space basis vectors. Our basis vectors are vector space of one forms. So that, when I take a metric tensor of that, this will become big. And you will see that this G alpha beta will be inverse of, and G will be a 2 by 2 matrix, sorry, 3 by 3 matrix, or 4 by 4 matrix. That will be an inverse of the direct lattice vectors. This is in general true. And also there is an additional feature for this metric tensor, that you can transform covariant components into contravariant components. That means it will transform vectors to one forms. You have a vector, it will transform to corresponding one form by using metric tensor. This is very, very general, because you can do this transformation. When you do this transformation in flat spaces, you don't find, you will get the same components. In special relativity, you will have some change, at least the time-delay component will switch its sign. But in general, three-dimensional spaces, what you see in mathematical physics books, you don't find any change. You will get the same vector, except it will become a row vector instead of a column vector. Components will not change. But in curved spacetimes, this is very, very important to understand that change from vectors to one form is always done by what is called a metric tensor. So, suppose if you have G alpha beta and you have a contravariant component A beta, then you get the corresponding covariant component A alpha. So this is a vector, this is a one form. So vector components are transformed to one form components, corresponding one form components using this metric tensor. Similarly, if you have a one-form component, A alpha, G alpha, G beta alpha is equal to A beta. This is one form, and this is vector. This is one form, and this is vector. Now this superscript, whatever we are writing, the contravariant metric tensor, this is called contravariant metric tensor. Contravariant metric tensor is the inverse of covariant metric tensor.
This is so in the case of only metric tensors or correct for any second rank tensor?
This is only true for metric tensor. Metric tensor is special in that way. It will transform a vector to a one form. But I should make this remark here that this will not transform the basis vectors. I have chosen this E alpha as the basis. Okay, so this remark is important because we have defined it in a particular way. Note that E alpha cannot be obtained by G alpha beta of E beta. I think it's not, so this notation is not correct, but okay, so this E alpha cannot be transformed. E alpha cannot be transformed to E tilde of alpha using metric tensor. Because, see, these are not the components, these are some different basis sets. We have defined this basis using a particular rule, this rule. Okay, so it cannot be transformed. That's the only remark that you have to keep in mind. Otherwise, the components of vector components can be transformed to one-form components by using metric tensor. This is an example of the second rank tensor, and an important example because it transforms. For example, in special theory of relativity, so let me just cite that example. G metric tensor is equal to -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. In 4D space. You write 1 here and -1 here. If you take three-dimensional Euclidean space and orthogonal matrices, G will be same as 1, 1, 1, identity matrix. So there is no difference between vectors and one forms in that case. Yeah.
You are saying that we don't transform the vector into one form. This G vector.
No, I am saying that this basis cannot be connected with the metric tensor. You have any vector, a corresponding one form can be obtained by a metric tensor, except for these basis vectors. We should not be under the impression that this basis can be transformed to corresponding one form using metric tensor. No, this basis, we call it as a reciprocal basis or a dual basis. It is defined by using the orthogonality every vector will be orthogonal to all other vectors except the first one. So that is this condition. This condition tells you E1 is proportional to all others except E1. E2, like that. So that's how we define that basis. So that basis is defined using that construction or that requirement, and so as I told you, basis is not unique. You can define any linear set of linearly dependent vectors as basis, but once you choose a basis in the vector space, correspondingly you can define a basis in the dual space. So these two are linked. You can choose arbitrarily any basis in the vector space. Corresponding to every basis, there will be a reciprocal basis here. Okay, so that is the connection.
So you wrote G value G46, the metric tensor.
Yeah.
Is it G superscript alpha beta or subscript?
In that case, there is no difference. That's what I am saying. Its inverse is same as itself. It's a diagonal matrix. Okay, but I will maybe what time we should break? Should break now. After the break, I will show you an example where G inverse will be different from G.
Is that the mixer type?
Yes, it is there. I will show you in one example how you get contravariant, covariant, and mixed metric tensors. Usually, mixed metric tensor is always trivial. It will be identity. Because mixed metric tensor, we have only second rank here, one subscript and one superscript. And we define our covariant basis using delta alpha beta. So, G alpha beta is always like this. So, it will be delta. So, mixed metric tensor, even in curvilinear coordinates, will be identity. But contravariant and covariant will be different. It will be different. The inverse will not be same. In flat coordinate systems, like in Euclidean space or in Lorentz space, you will have no difference between contravariant and covariant metric tensor. Okay, then we can stop.